Dear students, in this video we are going to learn the concept of phonons and its interaction with photons as well as with the lattice. So let's begin. We know that at absolute zero the crystal lattice is completely static. That means its atoms are fixed at the position and they are bounded with the covalent bonds with their neighboring atoms. So in the crystallographic structure where we studied lattice, Brevis lattice, reciprocal lattice, all these topics considered to be at absolute zero. That means there is no motion considered and the static is to be taken as a static system. But with the increasing temperature, this is not the case. If we consider a one-dimensional monoatomic lattice, as in this shown figure, there are 5 atoms which are identical, and if we consider any one particle, say this, then it will be having some equilibrium position. This equilibrium position means that when the particle is at rest, it stays in this position, just like a pendulum. When it is at rest, it is in its equilibrium state. But with the increase in temperature or any kind of energy which is being provided to the crystal, say it is optical wave which is passing through the crystal or anything else which disturbs the static system, there will be some displacement of this atom from its equilibrium position, and from the Hooke's law there will be a restoring force which will make this particle to oscillate on around its equilibrium position. But it's not only the wave or the temperature is affecting only the one atom, it is affecting all other atoms, and thus there is a continuous motion or oscillation of atoms, and the oscillation of these atoms are not in phase but they are having same frequency. So if we consider the collective oscillation of all the atoms in the crystal, it will form a wave which we call as acoustic wave. Now this wave is analogous to the electromagnetic wave which is produced by the variation of electric and magnetic field, but in this case what is varying, that is displacement of the atoms with time. So just like electromagnetic waves, acoustic waves also carries energy, and we know that quantum mechanically energy is always quantized. So just like we had photon as the quanta of energy of electromagnetic wave, there is another quanta of energy which we call as phonon, and they carries the energy of acoustic waves. So they carry the momentum which is and energy given by the expression E equals to h omega and P equals to k omega. If we define phonon, the phonon is a quantum of vibrational energy that describes collective and quantized oscillation of atoms within a rigid crystal lattice. Now here the two terms which I have highlighted is collective and quantized. Collective means that it's not only single atom which is vibrating and which is producing the wave is produced by the collective oscillation of all the atoms in the crystal, and the energy is quantized, and that packet of quanta of vibrational energy is called as phonon. It is a quasi particle because if it would have been a particle, then we would have considered single atom as a wave, its oscillation as a wave, but here we have taken the collection of particles that makes phonon to be a quasi particle, and just like photon, its rest mass is 0. Now we will be doing the mathematical derivation of how this phonon is affecting the interaction of photon with the lattice, and how the interaction of photon with phonon takes place. That means how the scattering of photon is affected by this phonon, which is the internal vibration of atoms. Also, I would like to mention here that in a crystal we are having electrons also which have been released from the positive ions in the lattice or crystal, and also there are some neutral atoms. So from the vibration of neutral atoms there is the production of phonons, and from the electrons and the ions which are charged particle there is the production of photon. So there is surely an interaction between photon and phonon.